Okay, ladies and gentlemen, let's then continue with Chapter 9, Chapter 9 on natural convection. The previous lecture was just an introduction on the mechanism of natural convection, and we have also showed you the Grashof number, this number. But how to get there, we didn't do the full derivation. There were some of the skips that I stepped, some of the steps that I've skipped. Okay. Now, it was all about the fact that there are three equations: the equation of mass, momentum, and energy. And you've derived them in Chapter 6. But in Chapter 6, the specific assumption was made that there's no buoyancy forces. So the only equation that had to be changed was the momentum equation. And in the momentum equation, where this Grashof number actually comes out of, this is not the new momentum equation. This is just a term in the momentum equation. So if you go and look in your textbook, you will see that before that you're going to get to an equation like this, where these are all the non-dimensionalized velocities in the different directions. But this is the term that appears there. And this is the Grashof number. So that is where it comes from, and that is how it fits into the momentum equation. And that is also why we have used the ratio of the Grashof number divided by the Rayleigh number to determine if a problem is being dominated by inertial forces, which is therefore a forced convection problem, or if it's a natural convection problem. So that is the background. Let's continue now with paragraph 9.3, natural convection on surfaces. And this is also a general paragraph, but it is going to end up very quickly with equations, and we are going to do two problems today, one that I hope to complete, and the second one I do not think we will complete, but which we will continue with the next lecture. So natural convection on surfaces are all about the fact that the Nusselt number, as I've mentioned to you in the beginning, is a function always of the Reynolds number, the Prandtl number, and the Grashof number. Okay. However, with problems which are really on, let's call it the extreme of natural convection, there's no Reynolds number, or it is very small. So the result is that the equations that we are going to use to solve natural convection problems in all cases are a function of the Prandtl and the Grashof number. Okay, so the Nusselt number is negligible. Now, there is not one general equation that we can use to solve all natural convection problems with. Just like with forced convection, we need the heat transfer coefficient. And to get the heat transfer coefficient, there are different equations that can be used, empirical equations, or we can get it from a graph or a table. And natural convection is not going to be different. It is all about the fact that you need to get the Nusselt number. To get the Nusselt number is some art in many cases. Obviously, you're going to use your textbook, but what is very important in the textbook is always the fine print. Okay, and I want to repeat it. The very important thing is not only about the selection of the equations, but the fine print. So many of you are going to start doing problems at the end of the textbook. You see, this is the geometry. You look in your textbook and you see, oh, yes, a table, let me use the equation. In many cases, you're going to make a mistake, because the table is somewhere there's text that says something about the table, and in the text they would say that in certain circumstances you must do this, in other circumstances you must do that. Or in the table itself, somewhere there's a fine print telling you something that you specifically should do. So it is all about being careful, but actually be very simple. So just be careful, but the principle is very simple. So you will see that the Nusselt number for natural convection problems are firstly a function of the geometry of the surface. And the surface can be a flat plate, it can be a cylinder, it can be a sphere, it can be the fins on the outside of an electronic component. So it depends on the geometry. Then also the orientation. And specifically the orientation with gravity. Because gravity has a big influence because it is all about buoyancy forces. So any geometry here on the surface of the Earth, its orientation is going to play a role. And also, the higher it goes up, the g starts becoming less and less, and at the stage when g is equal to 0, there's no more natural convection. So gravity plays a very important role. Then also the variation of the temperature on the surface. So is it a surface where it's a constant wall temperature, or is it a surface where there's a constant heat flux, or are there changes in the temperature? That plays a role. And specifically this temperature influences the properties, the thermophysical properties, the thermal conductivity, the viscosities, etc. All of that is specifically being influenced by this temperature or the representative temperature that we should use. Now, just like with forced convection, you'll see that in general, the Nusselt number can normally be described by saying it is equal to a constant multiplied by the Grashof number multiplied by the Prandtl number to the n. And where n is normally approximately equal to a quarter for laminar flow, and n is approximately a third for turbulent flow. And c itself is normally smaller than 1. Right, now I hope you've got your textbook here of Cengel and Ghajar, and if you do, please open it, because there's a table that we're going to use quite a lot now, and it is very important that it is table 9.1. So unfortunately, my laptop cable, I can't connect it to the data projector, so I am going to go to that table, but just on the video. So unfortunately, I cannot show it to you, so please just take a look in your textbooks. I will try to do both the textbook and the board at the same time. So if you can look at that table, you will see that in the table there are a few geometries. In the video, I think it is going to be a little bit too small, but it is a vertical plate typically, then it's going to be an inclined plate, then there's going to be horizontal plates, there's going to be a vertical cylinder, a horizontal cylinder, and a sphere. Okay, do you see it? And for each one of them, you will see that there is the characteristic length is given to you, how you should get it. Then also given is the range of the Rayleigh number, and then there are Nusselt number equations. In some cases, there is just one Nusselt number equation, and in other cases, the equation depends on the Grashof number, the range of it. So it is as simple as that. You have to use that. But it can be an art. So for example, the case of the vertical plate, like that. It gives, in the table, it tells you how you should get the characteristic length. And in this case, it is equal to L, where L is equal to that length there. Okay. Then it gives you the Rayleigh number range. And the first range is, for example, 10 to the 4 to 10 to the 9th. Okay. And the second range is 10 to the 9th to 10 to the 13th. Okay. Take note, there are at least 2 errors in this table. Okay. In your study guide, I've given you the information where you can get all the printing errors in your textbook. So please go and correct them, because you're going to use that equations, and if you didn't correct those equations, you're going to get the wrong results. So please take note of that. Okay, so it says that if the Rayleigh number is between 10 to the 4 and 10 to the 9th, then the Nusselt number is equal to 0.59 multiplied by the Rayleigh based on the characteristic length, L, to a quarter, and if it is between 10 to the 9th and 10 to the 13th, it is equal to, the Nusselt number is equal to 0.1 multiplied by Rayleigh to the 3rd. Those are the two equations. And then there's a third equation, which is a longer equation, and it starts with 0.825 plus lots of other terms. And in the fine print, it tells you this equation can be used for all ranges, and it is more accurate than those two equations. So, if you just want to make an estimate, I would in most cases use one of those equations, because it is just simpler to use, easier to use in making a calculation. Okay. Then, the next one is an inclined plate. An inclined plate. And again, they give you the characteristic length, and they tell you that in certain circumstances you can actually use the equations of the flat plate. And students find it very confusing. You won't find it confusing now. You'll read it and you'll say, that's great, until you have to do a problem. And then you're going to be stuck. And it is very confusing. You really have to understand what they're trying to say, and I'm going to explain it to you a little bit later. Okay, but in that equation, what they also say is, for example, except for the text, where they tell you that in certain circumstances you can actually use one of those equations, it tells you that G have to be changed to G cos theta. Okay, where that is the angle theta. And that theta is just valid between certain ranges. You see that? Okay, now I'm just going to make this a little bit larger quickly. So if you can look at table 9.1, it says for the inclined plate, the characteristic length is L, so that is easy. But then it says, use the vertical plate equation for the upper surface of a cold plate and the lower surface of a hot plate. Okay. But then it doesn't say about the other two cases that you can have, and that is going to be what is going to be confusing to you. Now, what is the rationale? What is going on here? What is going on here is that, remember, when we've looked at a vertical plate, we've said the boundary layer is going to develop like that. It's going to increase in thickness. Okay. Now, if we now have a plate where that side is the hot side, okay, and it is actually, in that case, let me rather put the thermal boundary layer on that side, and this side is insulated. Okay. If we start tilting the plate now, okay, you can see that that boundary layer is still going to develop like that. Okay, you agree? Until it is in that position there. Okay. And if it's in that position there, the flow would mostly be in that direction, going up. Okay. But let's suppose the hot side was at the bottom. Okay, so that is now the hot side, T hot. And now we start doing that. Okay, so the hot side is at the bottom. So what is now going to happen is that the flow also wants to move up. it don't want to just go up like that, and the result is that we're going to get flow patterns that is now going to start doing something, things like that. Okay. These ones, for example, if you've got a hot one at the top, or let's look at the case where this is the cold side, so that was cold. Okay. So if it is cold, the flow would typically do something like that. Okay. Or if you do it at an angle, flow would move up. Okay. So depending on the orientation of the plate, and in terms of which side is the hot side or the cold side, you can have situations where you're going to have a boundary layer that develops like that. And it's only for those cases where you can use that equation there. And that is what the textbook is trying to say. So if you've got a boundary layer that develops, okay, then you can use that orientation. Let's see if I can. Okay. So in general, I'm going to draw it like this. So you can have, for example, a hot plate. A hot plate. Let me just increase the angle a little bit, like that. So that's a hot plate. So if it is hot, then the boundary layer is underneath is going to develop, and it's going to increase in thickness. However, at the top, it's going to start doing that, but you're going to have flow like that. Okay. While if it is cold, a cold plate, then the boundary layer is going to develop that. It's going to start at that side and it's going to move downwards. And at the bottom, also going to have flow patterns like that. So I think what I've tried to show you here is maybe a little bit confusing. So summarize it with that too. Okay. So with a hot plate, it's going to develop like that. In these cases, it's going to develop, but then the gravity is going to force it up, like to go up. Okay. And if you go and look in your textbook, you will also see that the theta angle is only valid between, I think, 0 and 60, something like that. So the moral of the story with the flat plates is that that case and that case is not in Cengel. And if you go and look at the text, it will also tell you that, and it would say that you have to go and look in other literature to get those two cases. However, for this case and that case, Cengel, referring you to these equations in some cases is correct, and you can do that. Okay. So if you just read the text, you will not really understand, or the tables, you will not really understand what it is trying to say. Do you follow? Okay. Now, there's another case, and that is the case of the horizontal plate. Okay, now, for the horizontal plate, take note, this characteristic length here was also equal to L, where L is, of course, the length of the plate. Okay, so that is equal to L, the length of the plate. Now, you're going to have a case where you've got a horizontal plate. And that length might be Lx, and that length might be Ly. Now when you get to the Grashof number, you'll see you need to use a characteristic length. Now which characteristic length should you use? Well, it's in the fine print. So the fine print tells you that for a flat plate, you have to use the characteristic length in terms of the area of the plate divided by the perimeter. You see that? So again, look in your textbook. It is the surface area divided by the perimeter, and then depending on the ranges, and if it's the hot surface at the top or the hot surface at the bottom, depending on those situations, you need to select the correct Nusselt number depending on the ranges. However, what is important is you need to calculate your characteristic length, and then when you get your Nusselt number, to get your heat transfer coefficient, you have to use that characteristic length, otherwise you're not going to get the correct heat transfer coefficient. So everything, ladies and gentlemen, is in the fine print with natural convection, just like with forced convection. So please, you have to go and read it very well. You have to underline the parts which are important, and when you do a problem, please be very aware of that. Now, if you look at that table, you'll say, great, I can see all these cases, and now I can do a problem. Again, in the fine print, it will tell you that there are two cases for a flat plate, for example, and that is the one for the constant heat flux, and the one is the constant surface temperature. And in the one case, you have to treat it a little bit different. So again, it is in the fine print. So for example, the case with a constant wall temperature. So for constant wall temperature, if we look at the temperatures all over the plate, that would be a constant. Okay, so there's the plate, like that. Okay. In the fine print, it will tell you that for the case where you've got a constant heat flux, that has to be treated differently. For a constant heat flux, your temperature is going to increase linearly, as we've seen previously. So your temperature on the surface is going to do that. Okay? It's going to increase linearly. And what you then have to do is, you have to get this film temperature at the position L divided by 2. So which is halfway in the center. Okay? And then you have to use that temperature as your film temperature. Now normally when you start a problem like this, you wouldn't have this temperature, which means that you will have to guess a temperature, work the problem through, get the temperatures, and then iterate it. So this problem is specifically much more sensitive for your starting condition and this specific temperature here. Okay, so please take note. This is one that's where I can catch you out in the exam. Okay, for constant heat flux case, you have to be very careful for that. Right, that is sort of the use of table 9.1. Let's do examples. Now, although this textbook is divided into, in general, surfaces and then fin surfaces and many other, the principles that I've done with you is going to be exactly the same with all the geometries. So we are not going to do every possible geometry in the class. Okay. But all of them have in common two things. The one is, normally, the equation is something like that. You need to get it from a table, a graph, or an empirical equation. That's the first thing. And then the second thing is read the fine print. Okay, so that is what is important with all of them. So let's look at a long tube. And it's in an horizontal position, and its surface temperature on the outside is 90 degrees Celsius. Its diameter is 100 millimeters, its length is 10 meters, and the ambient temperature is 0 degrees Celsius. And the question is, determine the heat transfer rate from this cylinder. Okay. So the outer surface temperature is 90, the environment temperature is 0, tube diameter, or the diameter is 100 millimeters, and it's 10 meters in length. Determine the heat transfer rate. Okay. So if we just think of Grashof numbers, we can immediately see there's a viscosity value that we need, there's a beta value that we need, so we know the properties are always an issue with these things. It's one of the first things that we need to get, because as soon as you get them, you can start doing calculations. So, we choose the film temperature as the point where we're going to calculate the properties. And in this case, it is 90 degrees plus 0 degrees divided by 2, and that is equal to 45 degrees Celsius. Now remember, it might be that I give you the heat transfer rate and I ask you to determine the surface temperature, and then you cannot calculate the film temperature. What do? You guess. You just start with something, work it through, and then with that temperature, you redo the calculation if necessary. So 45 degrees Celsius, our fluid or gas is air. So if you go and look in table A15, you can get all the properties there for air. And the properties are, firstly, the thermal conductivity equal to 0.02699 watts per meter Kelvin. The Prandtl number is equal to 0.7233. And the kinematic viscosity is equal to 1.772 multiplied by 10 to the minus 5 square meter per second, and then beta. Beta, you'll see beta is not given for air. Okay. Now, if you think back of the theory, then you might remember that for an ideal gas, we can say it is equal to 1 divided by the film temperature. Okay. So that is what we're going to do here. It is going to be 1 divided by 273, take note, it's in Kelvin, plus 45. And if we calculate it, then it is equal to 0.003145. Okay, so table A15, and that's 100 millimeters. Okay. So let's calculate the Grashof number. The Grashof number is equal to G multiplied by beta, Ts minus T infinite, multiplied by L to the third divided by the kinematic viscosity squared. So everything is here. Let's calculate it. It's 9.81 multiplied by beta, 0.003145, multiplied by the temperature difference. The surface temperature is 90, minus 0, divided by the length, 10 to the third, divided by the kinematic viscosity, and that is equal to 1.772, multiplied by 10 to the minus 5 square. That right? Fortunately, I can see a few heads moving. Okay. Fine print. Okay, so let's look at the fine print. So yes, unfortunately, some of you don't have it there with you, but if you go and look for a horizontal tube, okay, so in this table 9.1, it's got that one, and somewhere here's the horizontal tube. But very importantly, it tells us that when we have to use the characteristic length, it must be the diameter, not the length. Okay? So, this is incorrect. Going to make a significant error if you do that. From 10 meters to 0.1 meters. Okay? So, then gives us the Grashof number as equal to 8.838 multiplied by 10 to the 6. Are you all with me? Okay. Now, we need the Rayleigh number. The Rayleigh number is equal to the Grashof number multiplied by the Prandtl. Of course, you could have done it directly. You could have just put in the Prandtl number there and directly determine the Rayleigh number. I prefer not to do it like that. And if you can calculate it, it is equal to 6.393 multiplied by 10 to the 6. You can see the Prandtl number is 0.7233, so it is just that multiplied by 0.7233, and then you get the Rayleigh number. Now that we've got the Rayleigh number, let's go and check. The equation says, or the table says, that there's an equation that we can use, and we can use it if the Rayleigh number is smaller than 10 to the 12th. Okay, and it says there, Rayleigh number, you see, D, 10 to the 12th, so we are fine, we are in range. We can use the equation. And then it gives us a long equation for the Nusselt number. And the equation looks like this. It is equal to 0.6 plus 0.387 multiplied by the Rayleigh based on the diameter to the 6 divided by 1 plus 0.559 divided by the Prandtl number multiplied by the power of 9 divided by 16, then everything to the 8.27, and then everything must also be to the second. Something like that. You see that equation? Let's just look at it in the textbook again. So there it is in the textbook. Nusselt is equal to 0.6 plus 0.387 Rayleigh based on the diameter to the 6 divided by 1 plus 0.559 divided by the Prandtl to the power of 916, also everything to the power of 8.27 to the power of the 2. This is the most complicated part in many cases with these calculations, getting these calculations correctly, and I'm not going to put in all the values. Here you can see is the Rayleigh number, we've got the Prandtl number, so it is just put it in, do the calcs, and then the Nusselt number is equal to 24.83. Right, so now the Nusselt number is equal to the heat transfer length multiplied by the characteristic length divided by the thermal conductivity. Okay. Now the Nusselt number in this case is based on the diameter. So this characteristic length is the diameter that we should use, not the length of the tube. So the Nusselt number is equal to 24.83. It's equal to the heat transfer coefficient multiplied by the diameter, which is 0.1, divided by the thermal conductivity, which is equal to 0.02699, from which we can get the heat transfer coefficient as 6.701 watts per square meter degree Celsius. Okay, now take note of the value. As you do these calculations, you should start getting a feeling for heat transfer coefficients. In chapter 1 of your textbook, there are certain guidelines, for example. They would say natural convection order of magnitude to about 10. So small values. So here you can see smaller than 10. If it's single phase fluid, hundreds to thousands. If it's condensation or boiling, to tens of thousands. So if you've calculated here 67,000, you must immediately know it cannot be possible. Okay, and it's very easy to make mistakes. Right, now that we've got the heat transfer coefficient, let's calculate the heat transfer rate, which is equal to the heat transfer coefficient multiplied by the surface area multiplied by the surface temperature minus the environment temperature. The heat transfer coefficient is equal to 6.701. The surface area is equal to pi multiplied by the diameter multiplied by the length. Pi multiplied by the diameter gives us the perimeter, multiplied by the length would give us the surface area for heat transfer. Multiplied by the surface temperature is 90, minus the environment temperature is 0, and then we can calculate the heat transfer rate as 1,895 watts. So about 1.9 kilowatts. Does that make sense? You all understand the problem? Do you feel comfortable with the result? There's a little bit of a curveball here, and that is you shouldn't feel comfortable with the results. Why not?
Constant surface temperature.
No, the constant surface temperature is not really the problem. They told us that. I know it's not really correct, but except for that, there's something else. Do you remember in chapter 1 you did radiation heat transfer? Okay. So somewhere in the work that we've done, we've neglected radiation heat transfer. But with natural convection, radiation heat transfer is usually significant. You cannot neglect it normally. Let's look at an example. So let's correct this quickly by saying this is the convection heat transfer. The convection heat transfer. And let's just go and make an estimate of the radiation heat transfer. Now, they didn't really give us lots of information to work on, but let's just go and calculate an order of magnitude. So the radiation heat transfer is equal to the emissivity multiplied by the Stefan-Boltzmann constant multiplied by the surface area multiplied by Ts to the fourth minus the environment temperature to the fourth. Okay. Now we don't have the emissivity, but let's assume it is equal to 1. It is usually smaller than 1, but that we're going to address in, I think, chapter 11 or 12. So we are not there yet. Okay, the Stefan-Boltzmann constant is equal to 5.67 multiplied by 10 to the minus 8. Right? The surface area is the same as previously. It is equal to pi multiplied by the diameter multiplied by the length is 10. So pi multiplied by the diameter is the perimeter. The perimeter multiplied by the length gives us the surface area. Multiplied by 90 to the fourth minus 0 to the fourth. Good. Why not? Great. You've remembered. So this temperature difference must be in Kelvin. Okay. So this should be equal to 273 plus 90 to the fourth, and this one should be 273 to the fourth. Okay? And then the radiation heat transfer is equal to 2,103 watts. If we look at these values, we can see it's significant. You see? Even although the emissivity might be 0.1 or 0.2, it is really going to influence your results significantly. So the thing that to remember with natural convection is usually you cannot neglect the radiation. Most of the problems that we're going to do in this chapter, we want the convection heat transfer because of the natural convection. Okay. So therefore, we should actually now say the total heat transfer rate is equal to the heat transfer rate of natural convection. Previously we've used a C there, maybe we should use a NC to indicate natural convection, plus the heat transfer rate of radiation. Okay. And if we add the two together, it is equal to 3,998 watts, so that is equal to 4 kilowatts. Obviously, by assuming the emissivity is equal to 1. It will be smaller than 1, but it gives us an indication of the order of magnitude of the radiation. Any questions, ladies and gentlemen? Is this problem clear to you? Great, thank you very much. Then we'll continue with the next problem with the next lecture. Thank you. Enjoy your day.